I'm John Loucaides from Intel, and this is Brent Holtsclaw.
Yep.
We're just going to present, we've got sort of a two-part series. Today we're talking about sort of an introduction to platform security. To this sort of an audience, I sort of feel weird about presenting an introduction to the thing that you guys all work on. But it is a interesting way to describe the threat model for the platform, and that's basically what we're actually going to present today. The threat model for the platform is fun, and we have a lot of fun with it. We look at researching different kinds of vulnerabilities and attacks and looking at what those attacks really mean in the real world. So if you look at what we're doing today, this week at the Plug Fest, we run out of our group the CHIPSECA project, which hopefully a lot of you already know about. But it's an open source project that allows you to test for specific known vulnerabilities. So we're here today with CHIPSECA on some USB sticks, and we walk around from room to room with our pile of USB sticks, and we basically walk into your room and we say, hey, can I run this on your computer? And I just plug this USB stick right here, if that's all right, and I'm just going to run this as root and do stuff. And we'll let you know. On the plus side, the tests pass. On the downside, you let me run stuff on your computer. Anyway, this is really fun, and I think the most important slide is this one, which Brent is going to take for us.
Thanks, John. So the legal notice. No computer can be absolutely secure.
There you go. All right. So we're really here to talk about threat model. We'll be here all night, though. The threat model, the way we think about it, or at least many of us think about it, as sort of why is it that you even bother to target firmware? Well, there are some pretty good reasons, and I think you can see examples of those reasons. Right. Maybe you can take it that way.
Yeah, so if you're already on the computer and you want to stay on the computer, if for some reason you can't get to something, or you want to get to it in a more stealthy way, or you just want to completely take it down, DOS it, PDOS it, whichever. So. In this slide, we wanted to point out that there's publications, NIST 800, which ones are they?
147.
147B and 193. So as you can see, people are starting to take the security more seriously. And Microsoft is starting to enforce security standards as well.
And it's like it's not some sort of erudite, unusual thing anymore. A lot of researchers have started piling on in this space. That's why you're seeing some of these larger organizations start to really talk about this. And so now it's sort of become, it's almost like firmware security is mainstream now. It's really interesting. And you're getting to this point where normal people have heard of the idea of firmware security.
So what are we actually talking about? We're talking about protecting your boot media, protecting your runtime firmware, and protecting your hardware configuration. And you can use, or the various classes of why you want to get there, they'll attack the various assets within the computer. So, anything else? Good. All right. And we've kind of laid out, there's your different classes of attackers. So you have your Ring 3 unprivileged attacker, your Ring 0 privileged attacker within software. And then within physical, we actually are starting to differentiate between limited physical, what you can do with 5 minutes, what you can do with the case kind of closed, and then unlimited, where somebody just has as much time as they need to find something, or they have as much access to the computer as they need. So if we take this and start putting it all together, what we want to do is find ways to protect, detect, and recover at the various stages and states of attack.
Yeah. So you can apply that to each of the assets that we were talking about. So you have sort of the assets of boot media, runtime firmware, and firmware configuration. And then you can apply that at each of the attacker privilege levels, sort of an unlimited or limited physical attack, or privileged and unprivileged software. So we're going to sort of walk through that, and we're going to walk through that by thinking about it in terms of interfaces. Now, all of the things in these slides are really about examples. They're trying to give you a model to extend. We're not trying to be exhaustive about every possible thing that we should have thought of. But you can look at, say, on the physical side, debug as a thing that is a really important critical feature, but also a really important attack vector if a physical attacker is within the scope. So how do you protect against that? How do you detect if that has been used or is being used? And how do you recover back to a secure state if somebody did manage to debug a system? Similarly, we usually look at the root of trust being the boot media that holds the system firmware. And so if I take, that's often on a SPI, if I take a SPI programmer, we're in this sort of physical space. And that's really not that hard. So that sort of comes into this sort of limited physical attack versus I don't need my evil lab that I basically have in my basement. But that's, you know, normal people have that anyway. The software side, you can look at sort of privileged and unprivileged interfaces, right? The privileged software interfaces, things that do like the out to B2 to call a software SMI, or maybe things that talk to some of the registers that should be in the protected spaces of MMIO, and a normal kernel would actually be expected to protect that. Versus the unprivileged interfaces that might be exposed through a software API to all applications. Things like some runtime services like variables, but also things that are exposed through device drivers. And that's where you get into some of the interesting bit. It's easy to lull yourself into a false sense of security here by thinking, oh, the OS will take care of this. Yeah, it probably does, but the thing is that you probably are exposing certain things through your device drivers that will allow you, if those things aren't written properly, to get at other resources. And so if you look at the ability to leverage a vulnerable device driver to access some hardware resource, that's a pretty legitimate attack. That's not that hard. You just need to find some side driver that does what you're looking for. In CHIPSECA, we do this too. So like we have on the slide read write everything, and that's a perfectly valid way of reading, writing everything. We do the similar thing in the CHIPSECA driver, and that's why we put warning messages all over it and say, you know, you might not want to do that on your production systems. Similar such things are possible. What we're going to do in the talk today is sort of quickly walk through these three assets, right? We're going to look at first the boot media, and we're going to look at sort of protect, detect, and recover. So first of all, the boot media, the attack would be writes to the boot media, right? Being able to overwrite system firmware or maybe replace a section or something like that. And so you have a protect, detect, and correct mechanism. You want to go for that?
Right. So for the protect, usually you're looking at the SPI controller, SMM-based protections, and just reducing the code base. For detect, whether it's hardware root of trust, UEFI secure boot, or measured boot. And then to recover, essentially some kind of capsule update or even independent hardware update.
And like the way that this tends to work is that you're relying on some element of the hardware, right? So in the case of SPI, you're looking at the SPI controller and its configuration, seeing that it's locked. You're looking at the SMM-based protections for the CPU-based protections. And generally speaking, in all cases, you're trying to reduce the TCB of things that have the privilege to leverage these interfaces. And so anything that you can do to reduce that is significant. Verified and measured boot sort of extend this forward. You deal with your root of trust being the firmware itself, and then as you're checking signatures or extending hashes into the TPM, you can bring that forward to the OS. What you want to do in a hardware root of trust is to actually take that first element, being the firmware, and move that into the hardware. And so there's different root of trust solutions for doing that. But the idea basically is as a detection mechanism most of the time. It could be a preventative mechanism in the sense that you have a thing in hardware like fuses or similar, but what you're guarding there is just that first root. Everything after that is still that chain of trust that needs to be continually extended. So as you think about protect, detect, and recover from the perspective of the different assets, you start moving from, okay, I have my firmware in that boot media storage location, to, okay, I set up this environment, right? And so I set up this environment, and that includes runtime firmware assets. In the case of x86, we're talking largely about SMM. So with SMM, you're dealing with a mode that is protected and separated from the regular execution. And so if you're able to gain influence or perhaps even take control of code executing from SMM, you basically have an elevation of privilege. You're able to do things that you weren't able to do as kernel ring 0. So there are different kinds of attacks. One is sort of a call-out attack, which we've presented before. It's the idea that you have this piece of code running at that higher privilege level, and it starts running and executing from something that's not protected as part of that higher privilege level. Okay, you shouldn't do that. So from a protect mechanism perspective, part of that is making so that if you ever do that, it's not going to work, right? You don't map pages, you use some sort of page table protections. In this forum a few years ago, we talked about no execute page permissions to be used for that sort of thing. There's a hardware check that Intel has. When you move from a protect to a detect, that's where you start doing things like fuzzing or using debuggers. And you realize that there are these code constructs in the firmware that need to be fixed. From a recovery perspective, when we find those things, we usually release a BIOS update. And so that sort of falls back on your update mechanism, often capsule. Another class of attack is a confused deputy. This is where you're basically using the code without modifying it at that higher privilege level, but you're telling it what to do. You get to say, I want you to write stuff to this address instead of that address. And if you get that level of power, you can sort of get into that. Oh yeah, I guess I'm sort of getting ahead of myself here. Another one would be malicious DMA. So the confused deputy basically is looking at it as you take these inputs, some of those inputs are then used to do the write. You can then manipulate where you're writing. You can bypass operating system protections because now you are running at this higher privilege level. You could potentially take over SMM execution by targeting SMRAM itself. The protection, if you're using like the latest Tiano core, is very simply to just only map the parts that you need into memory. That causes these other accesses to generate page faults, and then it doesn't present a problem. From a detection perspective, so that's sort of a preventative mechanism. From a detection perspective, we use a fuzzer. So in CHIPSECA, we implement this SMI fuzzer that will try and feed bad inputs to these things and try and get them to write outside of their protected location. There's also this idea of protecting against DMA. And so from the perspective of the runtime firmware, SMM, SMRAM is protected from the processor using these SMRRs. And then it's also protected from these external DMA devices using the TSEG range. And so one of the other things that you can do to try and enable protection across not just SMM, but the rest of the boot process is to start introducing the configuration of the IOMU earlier in the boot process. And so we have we have some open source available where we've done this on the latest Tiano core. We have a white paper that describes how this works. And it's really all about trying to prevent these other access vectors from getting execution early enough before you've locked things down, before you've done all of the setup that needs to happen to have the system be in a secure state. Do you want to do configuration? Or you want me to, that's cool. So the last asset is really about hardware configuration itself, which sort of bled into already.
Right. So within the hardware configuration, we're essentially going through to make sure you actually turn on the correct registers and register settings at the right places. So whether it's memory, controller, enable or disable features, it's mainly comes from configuration and locking guidance. So whether it's name your major manufacturer, they should have some guidance as to when to set it, what should be set, and why. So again, we use CHIPSECA to check the configurations of certain registers.
Yeah. So I mean, a lot of this is stuff that we implement automatically in CHIPSECA, and so a lot of the tests that you run when you just run CHIPSECA main are tests for hardware configuration registers, and a lot of that just might be how it's configured, but it's a lot of it actually comes down to did you lock it, and so that kind of gets into the recovery mechanism. If you misconfigured it and you reboot, it comes back in a certain way. You could recover it at a reboot, but generally speaking, what happens, you're going to run that same firmware again, so you probably want that firmware update that's actually going to change what it's doing behavior-wise in order to get those things configured properly. And so the point of CHIPSECA is really a detection tool to allow you to find the places that you don't have this done the way you want. And then you can use these recovery mechanisms, again, sort of relying on that firmware update capability to kind of get back to where you'd rather be. You want to talk about CHIPSECA?
So CHIPSECA's been out since 2014 now?
2014.
2014. Gone through a couple maintainers now. They're, let's see. It's the easiest way to describe it, yeah. So the easiest way to describe it is there's essentially two modes, a main mode which will run a suite of tests, or a util mode which you can kind of define your custom tests. But you'll write either a module or a tool. It'll read configurations based on your chipset and then implements commands. So the HAL is the hardware extraction layer, which exists as kind of a
layer of indirection, for you to rely on in a module rather than actually just calling individual MMIO regions or something.
Yeah, and then for every OS, there's a specific helper which essentially calls into the driver for the specific OS. Currently, it supports Intel hardware, and it's available for Linux, Windows, EFI, and OS helper, or OS X, sorry.
Yeah, so we try to abstract things in such a way that you write the test once, and then it should be reusable across all of those different platforms and all of those different operating systems. And it's an open source project, so the whole idea is that you all can contribute back to it and sort of extend it to handle some of the different areas that are of concern to you. And if you look at just a sampling of some of the tests that come with CHIPSECA, you can see that you are largely looking at these locks, these hardware configurations for, say, the memory controller. And each sort of test module maps to those set of configuration items. So you've got the memconfig module for the memory controller, SPI access for the descriptor access permissions, the SPI controller itself being locked and configured properly with SPI lock, et cetera, right? This is largely what a lot of the things in CHIPSECA will do. And so you sort of apply this concept. And so what we wanted to just put out there was this way of thinking about, you have assets. Specifically, you have boot media, the runtime firmware, and the hardware configuration as major assets, each of which you can think of being attacked by different classes of an attacker. If you think on the physical side, you can look at trying to handle an unlimited physical attack from me in my lab in my basement with all sorts of crazy equipment, but you probably won't get very far. You could probably extend that to something a little bit more tractable in a limited physical attack. if I have 15 minutes of quality time with your laptop, what can I do? But then you also have the software attacks, and that's where you're getting into sort of how do I protect, detect, and recover from an adversary that's running malicious code, either privileged or unprivileged on my system. And so if you apply protect, detect, and recover to each of these different areas, you can sort of classify and understand what it is you're doing for each of those assets. And then, so that was the intent of just describing each of those things and walking through it today. Sort of wanted to put a threat model out there so that it can be extended and sort of leveraged by others. Hopefully it is useful, and hopefully we can connect it up to tools and other techniques that we are also researching, both our team and I know across the industry. So that's the whole idea today. Thanks for having us, and hope you're having a great Plug Fest. When we come up to your rooms and we bring USB sticks, you know, congratulations. Thank you for letting us plug those into your systems and have all sorts of fun things to do with them. So, thanks again. Appreciate it.